Let's start with moment of inertia. It is measurement of how mass of a body is distributed about an axis. So if mass is near to the axis, moment of inertia will be low as compared to when mass is far away from the axis. And axis may or may not pass through the body. For example, here we have taken this body of mass m, and here we have taken two axes. One is passing through the body, other is not passing through the body. Okay, right. Now you can see that with respect to this axis, okay, moment of inertia is I1, with respect to this axis it is I2. Okay, now with respect to this axis you can see that mass is closer as compared to this axis, so we can say that I1 will be less than I2, because with respect to I2 mass is far away from the axis as compared to with respect to I1. Okay, now before we do some problems, some results of moment of inertia of basic symmetrical bodies we must remember for our easy calculations. Okay, so let's start with those results. The first basic result is the formula of moment of inertia for a point mass. So suppose you have this axis and at a distance r you have a point mass m. So what will be its moment of inertia? It will be simple mr square. So if you have point objects, you can just use this result and add to find the total moment of inertia. Okay, next is uniform rod. Let's take uniform rod of mass m, length l. Okay, let's take an axis passing through its center of mass. So its moment of inertia will be ml square by 12. Okay, now similarly you can take a rectangular sheet, uniform rectangular sheet, you can see that of length l and breadth b. Okay, now you can see that if you take this axis, this looks like a rod of length l. So what will be its moment of inertia? It will be ml square by 12. Whereas if you take this length, you can see that now it is similar to a rod of length b. So what will be its moment of inertia? mv square by 12. Okay, next is uniform ring. Now uniform ring, if you take, or you take a hollow cylinder, both will have same results. Okay, so we'll be using these two interchangeably. Okay, so uniform ring means mass will be uniformly distributed, and let's take moment of inertia about an axis passing through its center of mass. So it will be, let's say, uniform ring, mass m and radius r, so it will be mr square. Same will be the story for hollow cylinder. Again, this will be the axis. Okay, it will have the same result. Okay, next let's see uniform disk. So uniform disk, mass m, radius r. Again I take this axis which is perpendicular to the plane passing through its center of mass. Its moment of inertia will be mr square by 2. Okay, now whether you take uniform disk or solid cylinder, you will have same result. Okay, so solid cylinder will be like this. It is solid and this is the axis, mass m and radius r. It will also have the same result, so you should keep in mind. Okay, next is we can take hollow sphere. Okay, so hollow sphere of mass m and radius r, and I take an axis which is passing through its center. It can be any axis which is passing through its center. So its moment of inertia will be 2 by 3 mr square. Whereas if you take solid sphere, again of mass m and radius r, so this is solid. Again you can take any axis which is passing through its center of mass. Its moment of inertia will be 2 by 5 mr square. Okay, let's see some other values. Let's take the example of cone. So first of all, hollow cone. So this is your hollow cone over here, and this is the axis, so its moment of inertia will be mr square by 2. Solid cone, it will be again about the symmetric axis, 3 by 10 mr square. Okay, now with these values and with two theorems, you can find moment of inertia about different axes. So those two theorems are, first is parallel axis theorem. Now what is parallel axis theorem? Here you can see that if you take this body, let's say this is its center of mass and this is moment of inertia about an axis passing through the center of mass. So if you know moment of inertia about an axis passing through its center of mass, you can find moment of inertia about any axis which is parallel to it. So let's take another axis which is parallel to it at a distance d. Okay, right. So its moment of inertia I, now you can write it as ICOM, that is moment of inertia about axis passing through center of mass, plus md square. Okay, but remember this theorem will be applicable only when you have one of the axes passing through center of mass. You cannot take two parallel axes, none of which are passing through center of mass, and apply this theorem. So that is very important constraint, keep in mind. Okay, next is parallel axis theorem. Now parallel axis theorem, keep in mind, it is only applicable for 2D objects. That means planar objects. It is not applicable for 3D objects. This is the important constraint. Okay, now what it says is, suppose you have this planar plate. This plate is there, it is present on xy axis. Now about any point, what you can do is you can draw three axes, x axis, y axis and z axis. Let's say z axis is perpendicular to it. Okay, now you can find moment of inertia about these three axes. This is ix, this is iy, and about z axis it is, let's say, iz. Okay, so this plate is in xy plane. Okay, so now what this theorem says, this says that moment of inertia, sum of moment of inertia about two axes which is in the plane is equal to moment of inertia about an axis which is perpendicular to the plane, iz. So ix plus iy, x and y are in the plane. So if you add moment of inertia about this will be equal to iz, which is the axis perpendicular to this plane. Remember, this is valid for any point. Okay, it's not necessary that that point has to be center of mass of the body. It is valid for any point. But remember, the constraint, the whole theorem is valid only for 2D objects. It is not valid for 3D objects. Okay. Now here ix and iy may or may not be same. For example, if you take this square plate, let's take this point here. So you can see that this will be ix and this will be iy. Similarly, same square plate, if you take a point here, now you can see that this will be ix and this will be iy. Okay. Now in this case, you can see that mass is symmetrically distributed with respect to x-axis and with respect to y-axis, or with respect to this axis and this axis. So therefore, when mass is symmetrically distributed about two axes, here ix and iy will be same. And therefore, this I can write it as iz by 2. Iz will be what? Moment of inertia about this axis. Okay. Whereas in this case, you can see that mass distribution about x-axis and about y-axis is not symmetrical. Okay. So therefore, here you can say that ix is not equal to iy. Okay. Ix is not equal to iy, but still ix plus iy will be equal to iz. Iz is what? Moment of inertia about an axis which is perpendicular to it. So this you should keep in mind. Okay. So let's do some questions so that we can understand the application of these theorems. Okay. So let's take one question. Let's take a disk, uniform disk, mass m and radius r. So here you have this disk, mass m and radius r. Now I am marking some axes about which we have to find moment of inertia. Okay. Let's start with, this is I1, this is I2. Let's say about this axis I3, about this axis it will be I4. Okay. So let's find moment of inertia about these axes. Okay. Now I1 we already know that result. I told you to remember. So I1 will be what? This is a disk uniform disk, that means mass is uniformly distributed, so it will be mr square by 2. Now I2 directly I can find using parallel axis theorem. As you can see that these two axes are parallel and one of the axes is passing through center of mass. So I2 I can write it as I1, which is ICOM plus md square. D here will be r. Okay. So its result will be, if I put this value, this will be 3 by 2 mr square. Now next is what? Let's try to find I3. Okay. Now you can see that I1 you know, and similar to I3 you can draw this axis also. Okay. So now you can use perpendicular axis theorem. These are two perpendicular axes, and the figure is symmetric with respect to these two axes. Okay, right. So let's call this as I4. Okay. So now I4 I have already taken, so let's call it as I5. Okay. So now you can see that if you apply perpendicular axis theorem about this point, you can see that I3 plus I5 must be equal to I1. Okay. And since figure is symmetric with respect to I3 and I5, so I can say that I3 must be equal to I5, which must be equal to I1 by 2. And I1 I already know mr square by 2. So this will be mr square by 4. Very simple. Okay. Now the remaining is I4. So if you know I5, again you can use parallel axis theorem because this axis is passing through center of mass. So I4 you can write it as I5, which is an axis passing through center of mass, and this is parallel to it, so plus md square. So it will be plus md will be here r. So I can put the value of I5 here, I'll get the value of I4. So you can see that problem becomes very easy if you remember some results and apply this perpendicular and parallel axis theorem correctly. Okay, so keep this in mind. Let's do couple of more problems. Let's take a semicircular disc. So this is a semicircular disc, mass m and radius r. Okay, and let's say I want to find what will be the moment of inertia about this axis. Okay, now about this axis you can see that this figure is not symmetric. Okay, so what we do is here we try to do it symmetrically. Okay, when I know the result, when it's a complete disc. Okay, so what I do is here half disc is given. So what I do is the other half I'll draw. So this is our first half which is given. Other half, let's say I draw. This is the second half. Okay, right. So if its mass is m, its mass is also m. So now you have a uniform disc of mass 2m. Radius remains r only. So okay. So for this total disc, you know what is this moment of inertia? Yes or no? What will be this moment of inertia? Disk formula directly I can apply, which is mr square by 2. Here m will be total m, which is 2m. So 2m r square by 2. R is as it is now. Okay. So this is nothing but mr square. Now remember here this is the moment of inertia of this complete disk. Here we have half of this disk, and by symmetry you can see that contribution of upper part and lower part will be same. Okay, so moment of inertia due to each part will be what? So I can say that moment of inertia due to each part will be half of total moment of inertia. So which will be half mr square. Okay, so keep this result in mind. This can be applied for a semicircular ring, or you can take a hemisphere also. Okay, right, that is nothing but half of the total sphere. So this logic you can apply. Now let's see one application of this. Let's take a hemisphere. So this is your hemisphere, something like this, of mass m and radius r. And let's say we have to find moment of inertia about this axis, which is tangent to the uppermost point. Moment of inertia about this axis. Okay, right. So now based on previous question, what I can do is, first of all I can find moment of inertia about this axis. Same logic, the other half I can reconstruct, and now moment of inertia due to each. Okay, I can know by finding the total moment of inertia. What will be total moment of inertia? This mass will be m. So about this is an axis passing through center of a solid sphere. So its moment of inertia will be 2 by 5 total mass, which is 2m. Okay, r square, right? So this will be r square. Okay, so 2 by 5 mr square na. So 2 by 5 total mass I have taken, which is 2m r square. Okay, now contribution of each will be half. So due to each, what will be its value? It will be half of it. So half of it will be 2 by 5 mr square. Okay, so that means about this axis I know what is moment of inertia. Okay, about this axis I know moment of inertia is 2 by 5 mr square. Now using this, can I directly find moment of inertia about this axis, because these two are parallel? So answer will be no. Why answer will be no? Because here we can see that here none of the axis is passing through center of mass. We know that in order to apply parallel axis theorem, one of the axes must be passing through center of mass. So for that, one little innovation we have to do, we have to find where center of mass is located. Okay. So here we'll say that we very well know for this solid hemisphere, center of mass is at a distance 3r/8. So this distance is 3r/8. Let's call it as d. Okay, right. So now what I can do is, let's take this. This is nothing but moment of inertia about an axis which is passing through center of mass. Now I can relate these two very easily, as well as I can relate these two. So indirectly I'll be able to find I. Okay. How can I relate these two? Very simple, parallel axis theorem. So what I'll write, I, which is 2/5 mr square. This is equal to ICOM plus md square. So d is nothing but 3r/8. So this will be md square. D here we have taken 3r/8. Okay. Now using this result, you will find ICOM. Now similarly, parallel axis theorem you can apply between these two axes also. Okay, so let's apply parallel axis theorem between these two axes. So I will be equal to, which I need to find, this will be equal to ICOM plus, now this will be the perpendicular distance between the two axes. So if total is r and this is d, so this will be r minus d. So m r minus d whole square. Okay. So what you'll do is, it's now very simple. This ICOM from this equation, you'll just put it here and you'll get the value of I. So you can see that this complicated looking problem becomes very easy once you have applied these theorems, and some results it's better you remember. Okay, you must prove it once, but after that you must remember those results. Thank you.